Welcome to the third video in our quantum mechanics series, where we will dive deep into one of the most fascinating and mind-bending fields of physics. Today we are diving into something so bizarre, so counterintuitive, it might make you question everything you thought you knew about reality: the wave-particle duality of light. This mind-bending phenomena isn't just a quirk of nature, it's a cornerstone of quantum mechanics. Today we will explore how light behaves like a wave in one moment, a particle in the next, and why this strange duality is as perplexing as it is revolutionary. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to the third video on understanding quantum physics. First, we start what is called the wave-like nature of photons. Now, once we start with the wave-like nature of photons, first of all, I would like to show you that in the earlier video, I described and mathematically tried to derive the equation of what is called the Compton effect. Now, the Compton effect actually confirms that photons behave like particles. If you have not seen this, you can go to my channel Physics for Students. I'm putting it also on the I button. So as it confirms the photons that behave like particles and how do they scatter, the angles, etc., it is not clear how the photon also can encounter something which is called a wave-like properties of electromagnetic radiation. Remember that this is still the classical era where we are quite certain with what we call the corpuscular theory of light developed by Isaac Newton. Now, this was going on in a kind of a dilemma that Compton effect proved that the photons behave like particles, but it was not until this person, Thomas Young, who first demonstrated this phenomena. And he actually indicated that light consists of waves. Now, he actually believed it to be the demonstration that Christian Huygens, whose wave theory of light was correct. So, Thomas Young believed that Christian Huygens' light theory was correct, and the experiments sometimes referred to as Young's experiments or Young's slits. Now, this is the name of the book, which is called the Treatise on Light, which are explained on the causes of that which occurs in reflection and refraction. This is a book written by Christian Huygens that was published in around 1690. And this book describes Huygens' conception of the nature of light and propagation. So what we understand from here is that unlike Newton's corpuscular theory, which was presented in his phenomenal writing Optics, Huygens conceived light as an irregular series of shock waves, which are coming and going, which proceeds with very great but finite velocity through the ether. Remember, during that time, the concept of ether was still there, and it is something which is similar to sound waves. Now, confirming and believing on Christian Huygens' hypothesis, Thomas Young developed what is called the famous double slit experiment. So, this is a kind of a modern version of the double slit experiment. The old ones I am not considering. So, as you can see that Young passed light through two closely spaced slits and observed the patterns which formed behind the screen. So, here is an electron gun, which as I told you is a modern version. These are the electrons. So, I have magnified and showed you down with the down arrow that these are the electrons, and what it comes that instead of seeing two bright lines corresponding to the slits, which is as per the corpuscular theory of light, he observed as interference pattern of alternating bright and dark fringes. This is a black and white photograph, so it is not clear, but if you can go to internet and search out, so you will see that there are interference pattern. So here, as I pointed out, that these are the wave-like disturbance from the two slits interfere constructively and destructively. Just to give you an idea of what is constructive and destructive interference, here you can see on the in this diagram that these two waves, they add up, and this is what is called a constructive interference. These two cancels out and adds and creates a kind of a straight line. So this is a destructive interference. So Young's experiment was basically a turning point because it provided strong evidence for the wave nature of light. And how it came? It came out of the constructive and destructive interference, which is very something very central to the wave theory. So it laid the foundation later on the wave properties of light, such as diffraction and polarization, which we will take up later. So this is actually the basic experiment which was done, and as you can see that light shines, it goes through it, it creates a constructive destructive interference, and on the back screen you can see that there are alternative bright and light dark fringes. So we will just take the same photograph from here and we will see that what are the important things which comes up. I mean to say, what are the conclusions that we can see from this part of the experiment. So here you can see in the basic experiment there's a coherent light source such as laser beam illuminates a plate pierced by two parallel slits. Then the light passing through the slits is observed on a screen behind the plate. Third, the wave nature of light causes the light wave passing through the two slits to interfere, producing bright and dark bands on the screen, a result that would not be expected if light consisted of classical particles. So as I told that the corpuscular theory of light is now under the question because it produces bright and dark bands. So however, the light is always found to be absorbed to the screen at discrete points as individual particles, remember not waves, and the interference patterns appears via the varying density of these particles hitting on the screen. So the result would not be the same as expected if light consisted of classical particles. So this is, I would say, step by step what we get from the wave-like nature of photons and the double slit experiment. What becomes also important now, this is a better kind of a picture. You can see this is actually the double slit apparatus that creates the interference pattern. These are basically the discrete packets of energy known as quanta, which I was telling that how would you see that light or particles like electron interacts with the detector and creates kind of a patch. So this is where the packets of energy are there. And light, for light, these packets are called photons. They are individual particles and the interference pattern emerges because the probability of detecting a photon or electron at a particular point in the screen is governed by wave-like equation. We don't know what is wave-like equation because Schrodinger have not come into the scene. What we are seeing is just the observations, and the physicists during that time, early era, was trying to get a kind of an understanding, and from that what would be the deduction, what could be the inference that was being done. So the most vital point, number one, is that the discrete points of detection reveal the particle nature of light or electrons, and the interference pattern on the other hand arises from the wave-like probability of distribution. So it is interfering as wave-like, but it is producing something particle-like. So that was something which was very important in the history of quantum mechanics, or you can say as the development of science, that Young's double slit experiment first created a doubt that how can this happen. I mean to say, it's a kind of a confusion. Still the mathematics was not there. Still the equations were not being governed properly. But this was what is the wave-like nature of photons. Remember that the Compton effect, which I described in the earlier video, that came much later. I should have actually described before this Young's double slit experiment, but the Compton effect. So Compton effect was done into the 19th century when the instruments were far much better. Anyway, so coming to this pattern, this is a computer generated, I would say, a diagram. So here you can see the pattern formed by 100 quantum particles. Next you see pattern formed by 1000 quantum particles. And now you see pattern formed by 10,000 quantum particles. So what I am trying to show you is that as the number of quantum particles increases from 100, 1000, 10,000, the interference patterns becomes more and more pronounced. So initially, as you can see in this on the screen, that with few particles the pattern is very random. However, with more particles the pattern emerges clearly showing distinct bands of higher and lower particle density. So here from this diagram what we can understand is that this experiment highlights the quantum nature of particles, and the experiment demonstrates the wave particle duality of matter. Particles can behave both like particles as well as waves depending upon the experimental setup. So as you can see, the number of quantum particles increases, the pattern emerges in a different way. Now, this is basically what is called the wave-like nature of photons. Now, before we go to Einstein's photoelectric effect, there's one gentleman who first detected the photoelectric effect, although he didn't went forward and analyzed why this anomaly was found. And that is what we are going to look into, the photoelectric effect. And this is something which we are first going to look, and then we will describe more on that. Now, starting from Maxwell's equations, the set of 4 equations, you can even go to my channel and select a very interesting video which has become popular, which is called Maxwell's History. It was not 4 or 8 equations, a set of 20 equations which Oliver Heaviside later summarized into 4 equations. So the first breakthrough in unification, obviously after Newton, came from Maxwell. He unified electricity and magnetism into a kind of a single framework which are called Maxwell's equations. So the formulation was done. This animation actually shows how electricity and magnetism they're going just like friends. But the problem was that this light is an electromagnetic wave and it constantly oscillates electricity and magnetic fields traveling through space. But how to demonstrate? I mean to say, this was theoretically done in some way, but how to demonstrate the existence of electromagnetic waves and confirms Maxwell's these equations. Now, in order to do that, we come across this gentleman who just lived for 36 years, unfortunately, great mathematician physicist Heinrich Hertz. Now, while Heinrich Hertz never went forward to detect photoelectric effect, history says that he was basically trying to confirm Maxwell's, equations are actually experimentally can be proved. But in order to do that, he came across something phenomenal. We will look into that. But in order to prove that, Heinrich Hertz came into the scene. So this is actually what is called the original instrument. We will just look into that, what this schematic diagram tells. So Hertz was actually investigating electromagnetic waves, confirming Maxwell's theories. So in 1887, while working on this apparatus for generating and detecting electromagnetic waves, he detected what is called a very unnatural phenomena. Let us look into this diagram and let us understand. Here you can see these G and E, these represent batteries, and that provide the power source of the experiment. This T is basically the switch through which the controls the flow of the current through the circuit. This O is basically, and others are metal spheres which are attached to the rod. When a spark jumps between them, it generates electromagnetic waves. And R, this is another metal sphere connected to a metal rod. It acts as a receiver for the electromagnetic waves. So what happens is that when the switch T is closed, a spark jumps between the spheres, generating electromagnetic waves. And these waves travel through the air and reach the receiver sphere R, as I have mentioned in a blue box. And the waves induce a current in the receiver spheres, causing a spark to jump between the sphere and the metal rod. So what we found from this experiment is the existence of electromagnetic waves. Just as Hertz targeted to experimentally prove Maxwell's equation, he was very successful. And he also showed that these waves could travel through the air and could be detected by a receiver. So this is actually what was done. Now after this, what the anomaly that came in is this. Now, in what Hertz did was that he took a ultraviolet rays, and this is a kind of a metal surface, and these rays are now hitting it over. So, and it is what it is doing, it is emitting or ejecting an electron. Now, classically what happens in the classical wave theory, the energy of the light is proportional to the intensity, because the intensity represents the energy carried by electromagnetic waves per unit time, and this is the equation. I is the intensity, mu naught is the permittivity of free space, c is the speed of light, and e is the amplitude of the electric field. So here it says that in classical view, increasing the amplitude, the E of the wave, increases its intensity, which in turn increases the total energy of the light. And but this won't apply for photons. Remember, we will see that how it emerges. So what we can see classically is this, that energy of light should depend only on its intensity, not on its frequency or wavelength. Now, when this ultraviolet light was shined on a metal electrode in his spark gap apparatus, it enhanced the production of sparks. So, according to the classical theory, the energy of light should depend on its intensity, and what Hertz observed was that only high frequency ultraviolet light had this effect. Lower frequency visible or infrared did not, regardless of how much intensity you produce. So from here what we understand is that light as a wave should transfer energy gradually to electrons, obviously, implying that increasing the light's intensity would obviously eventually cause the more of the ejection of electrons, which was actually not happening. So this photoelectric effect, the observation was done by Heinrich Hertz, although he was trying to prove Maxwell's equation experimentally. So the more, as per the classical theory, the more will be the intensity, the more will be the ejection of the electron. So what we get are three important things with the classical physicists made. Number one is the higher the brightness or the intensity of the incident photon, the greater the energy of the electrons that are emitted from the surface. I mean to say it should be. Second is that a light wave of any frequency should be able to knock off electrons, provided a reasonable intensity is made. And third is that if the incident light is low, it's a very low intensity, low brightness, low intensity, then the metal surface must be continuously exposed until enough waves are there which strike off the electrons, strike off the surface of the metal to eject the electrons. So these are the classical prediction. Now what Hertz actually concluded, taking the same kind of a UV ray which is striking the metal surface, ejecting the electron, is this: that when the ultraviolet light was shining on the metal electrode in a spark gap, it enhanced the production of sparks. The enhancement suggested that light was influencing the ejection of electrons, obviously, and it is making the easier for the circuit to conduct. Third is that according to classical wave theory, the energy of light should depend on its intensity, and he observed that only higher frequency had this effect while lower frequency is not. Then what is the problem? Is it that only high frequency is knocking off the electrons, low frequency is unable to do? So we come to this understanding that Hertz did not relate this phenomena to the ejection of electrons. He was just focusing on Maxwell's predictions. And while Hertz observed this effect, he never made an attempt to provide a theoretical explanation. Later, the connection between light's frequency and the ejection of electron was established by Philip Lenard, who won the Nobel Prize in Physics, and Hertz's experiments was pivotal because they confirmed the existence of electromagnetic waves. So Hertz actually detected the anomaly, but he did not went forward to correct it, and later it was proved by Philip Lenard, but he successfully proved the Maxwell's theory, the equations are correct. So here is the summary. Although Hertz did not investigate this anomaly, this observation of the photoelectric effect revealed the limitations of the classical wave theory, and it became a cornerstone in the development of modern physics. So here is a summary that what were the importance. Obviously, when an anomaly is detected, there should be an importance which would lead to another area of physics. So importance of Hertz's observation, number one was that it demonstrated that light has both wave-like and particle-like properties. Second, it provided strong evidence in terms of the quantum nature of light leading to development of quantum mechanics. Also, one of the first phenomena that classical physics actually had limitations to explain, and along with blackbody radiation atomic spectra, it catalyzed it, I would say, it kicked off the entire quantum revolution. Now, before we come to the photoelectric effect, which actually when Einstein came in and developed this, which Hertz actually have left it, we need to understand one simple concept which is called what is a work function, because this work function will be later related to photoelectric effect. Now, if I go by this simple definition of work function, it is basically this, that it is the minimum energy, which is required to knock off an electron off a surface of a material. So you can read the first line, which is based on thermodynamical statement, but I would say it is the minimum energy which is required to knock off. But remember that it depends on certain materials. That means different materials would have different work function. So it depends upon the material's properties. For example, potassium would have a work function this much, gold would have a work function of this much, and so on. So remember that work function is the energy. If you, for example, if you're imagining as electrons sitting inside a building and the building has a door with a certain energy barrier, so the work function is the energy which is needed for someone to open the door and step inside. The work function is typically expressed in electron volts, which is this, and the work function W is given by this equation. Now hold on, I would just like to explain this equation a little bit so that your concept is much clearer. So this W is basically the work function. Minus E obviously is the charge of the electron. This is basically what is called the electrostatic potential. And this together is the energy of an electron at rest in the nearby vacuum, nearby the surface. And this one, EF, is basically called the Fermi level or electrochemical potential. Now let me explain you in very simple terms. The Fermi level is basically called the highest energy that electrons occupy in a material at absolute zero temperature. You can just think it as it is like the cutoff point for electron energy. Electrons below the Fermi level are tightly bound. Electrons at or above are free to move. So this is how actually the equation looks. Now why I am telling you this equation, it will soon become clear. Now if I go by the key equation, that is, which is this one, what I get is that if I shine a kind of an incident photon, incident ray, this is the incident ray which is coming on. So we know that the energy of the incident photon is by E equals to h nu, where h is the Planck's constant and nu is the frequency of the incident light. Now, if this exceeds the work function, that means E is greater than or equal to phi, then only the electrons are getting ejected from the surface. That is why it is important. And if E is less than phi, what will happen? No electrons will be ejected from the metal surface, obviously, because the work function energy is less than the work function. So the energy required to free an electron from the metal is this one. And this is this equation, as you can see on the screen, K equals to h nu minus 5, where K is the kinetic energy, h again is the Planck's constant, nu is the frequency of the light, and phi is the work function of the material. So what I'm trying to tell is that the work function actually determines the threshold frequency for a photon energy to eject electrons. So I've written this as h nu underscore threshold is equal to phi. So this is a important concept. Now, in order to knock off, for example, if the incident ray is falling and the electron is knocking off, we call that E photon is equal to h nu. That means for an electron to be ejected, the energy of the incident photon must be at least equal to the work function, which is h nu greater than or equal to phi. If h nu again is less than phi, no electrons are ejected. When h nu is greater than phi, the excess energy h nu minus phi is converted to the kinetic energy of the electron, ejected electron, which is k equal to h nu minus phi. And if we get the minimum frequency of light, which is v underscore threshold, needed to eject the electron, it is determined by the work function v threshold equal to phi upon h. Now you need to just keep this equation into mind, because I'm going to come back to this equation. This is what is called a work function. This is important in terms of understanding photoelectric effect. Now we come to Einstein and photoelectric effect. I will just explain Einstein's famous contribution. And remember, he won the Nobel Prize for photoelectric effect, not for general relativity or special relativity. So in 1905, the paper, I'm not going into the details, he built upon Planck's quantum theory, and he proposed that light is made up of discrete particles which are called later photons. So E is actually proportional to nu. That means energy is proportional to the frequency. Nu was replaced because we need a constant to replace a proportionality, and it is called h, that is the Planck's constant. So what we get is that energy is now relative to frequency, or technically we should say proportional to frequency, and energy is also quantized from this famous equation. So the same kind of a setup, if you take of Hertz, there is a metal surface and this one is striking the metal surface, ejection of an electron happens over here. Now you see, as I was telling, this is important, E should be greater than equal to phi. So the minimum energy required to eject the electron from the metal, the electron is emitted with the kinetic energy, Ke equals to h nu minus phi. Now remember, later Einstein's explanation was confirmed experimentally by Robert Millikan. So this is actually very central to our understanding, because this is the first phenomena that classical physics could not explain, which confirmed or set the stage for a new theory which is called the quantum framework or quantum physics. Now if I go by the key equation, let us understand a little bit mathematically, which will be very easy and clear. The energy of the incident photon would be equals to h nu. I'm not explaining that. The energy required to free an electron from the metal would be h nu equals to, phi equals to h nu upon 0. And this nu 0 is the threshold frequency as this is described. So if the photon's energy exceeds the work function, it would be this. And if h nu is less than equal to phi, no electrons are ejected. And remember, whatever amount of intensity that you put it is not going to eject an electron because it has come down the threshold level. And there is something which is called a stopping potential. This is the measure of the maximum kinetic energy of ejected electron. A reverse potential V is applied to stop their motion, which gives by this equation. Now all through this time it is all good, all set and nice and fine. But have you considered that what would happen using a weak light source? We are using a strong light source. We are seeing this and that which is happening. So what would happen using a weak light source? And that is what I am going to explain you in the next part of the video. Now, according to classical physics, so let us see this is an example, a kind of a thought experiment, metal surface, and this is a weak light intensity, weak light source. That is why I have highlighted it in gray. So according to classical physics, an electron would keep on, remember, I am considering a weak light source. So what would happen? It would keep on absorbing energy at a continuous rate until it gained a sufficient amount that then it would leave the metal. Now, if this argument actually holds true, then using a very weak radiation, the photoelectric effect would take a very, very, very long time, obviously, possibly hours, until an electron gradually accumulated the necessary amount of energy. The conclusion, however, shows a disagreement. The conclusion shows a disagreement with the experimental observation. So I have put the thumbs down. So experiments were actually conducted with a light source that was so weak that it would even take several hours for an electron to accumulate the energy needed for ejection. And yet some electrons were observed to leave the metal instantly. Now how can this happen? So further experiments showed that an increase in intensity, I mean to say brightness, for example, alone can in no way dislodge electrons from the metal. But by increasing the frequency of the incident radiation beyond a certain threshold, even if the light is very weak intensity, the emission of electrons starts immediately. So this is a very revolutionary concept. I again repeat that the experiments were made in such a way that it has been left for a very, very long, several hours for an electron to accumulate the energy, and yet the experiment showed that some electrons leave instantly. And the experiment showed that when an increase in intensity alone can no way dislodge electrons from the metal, but by increasing the frequency of an incident region which is beyond a certain threshold, even at very weak intensity, the emission electrons happens immediately. So these experimental facts indicate that the concept of gradual accumulation or continuous absorption of energy by the electrons, as predicted by classical physics, is wrong, erroneous, or you can say it as a kind of a limitation. So what we can get finally is that this is called the photoelectric equation, where you can see this h nu is the energy of the incident photon, w is the work function, and k is the kinetic energy. So this actually gives a very, very good proper explanation, the experimental observation, that the kinetic energy of the electron increases linearly with the incident frequency. This graph actually shows this one. It continuously increases. It goes on increasing and so. And this equation is something which actually shows the parts which was derived by Einstein and gives a proper explanation to the kinetic energy being growing linearly. And in this equation you can see that nu naught equals to W upon H, or if you can recall just at the starting of the video, the threshold is equal to phi upon H. Both of them are similar, just using different notation. This also shows that why no electrons are ejected from the metal until and unless nu is greater than nu naught. Since the kinetic energy cannot be negative, the photoelectric effect cannot occur when nu is less than nu naught, regardless of the intensity of the radiation. So this is actually kind of a proof, mathematically, physically, or through experimentation, that even using a weak light source, what actually things happen. Now, if you look into this linear progress, then you will see this is the kinetic energy, this is the frequency, and this linearity actually indicates a direct proportionality between the kinetic energy and the ejected electrons, which is given by this kind of an equation. So we come last that after all of these things accumulate ultimately to the benefit of something. So what is the importance of the photoelectric effect? The first thing is that E equals to h nu demonstrate that light behaves as discrete particles and not just waves. Also, the classical wave theory could not explain why light frequency, not intensity, determines electrons ejection. We found great application in terms of photocells, solar panels and light sensors using the same photoelectric effect. And finally, Albert Einstein won the Nobel Prize in Physics. The Nobel Committee awarded for his explanation of the photoelectric effects as provided a very critical evidence for the quantum nature of light. Lastly, I would like to say this, that Einstein, although made significant contributions to Brownian motion relativity, the photoelectric effect directly bridged experimental observation, which is done through experiments, instruments, and quantum theory, making it more and immediately influential. Maybe that was the reason that he won the Nobel Prize in this, but not in revolutionary theories like special and general theory of relativity. So we take a pause in today's video. We are done with the third lesson. Thank you very much for watching this video. If you've liked, please do subscribe on my channel Physics for Students and click on the bell icon to get all the notification from Physics for Students. This is my email ID, and you can always subscribe to my other channel, General Relativity Explains. You can follow me on my Facebook, LinkedIn, Instagram and Twitter account. Physics for Students will be soon back with more surprising videos and coming up very quickly with a wonderful podcast with Dr. Federico Silvetti from the celebrated Durham University, United Kingdom, talking about quantum chromodynamics and strong particles forming the Standard Model. See you soon. May the good Lord be with you.